Hello YouTube, De-bodgery here. Welcome to EV Components Review. On the screen today is a BAC4000. And we're going to do an overview of the thing and compare it with the BAC8000 since I have one that I already took apart in the background. Anyway, these two controllers are really similar with a couple of exceptions, and I'll get to those as I go along. There is a lot of cloning going on between these two. Not really very surprising. Both of them made by ASI. That the designs are so incredibly similar because they are really similar. Anyway, I'll just talk about the differences first because those are few and far between. So 24 MOSFETs, 36 MOSFETs. That one's the biggest one. The way current sensing is done here and current loops here. And I'll get into this a little bit later, but yeah, different type of current sensing, similar specifications for these as for these ACS current sensors, but just a different current sensor type, and I'll explain why one is better than the other. And the other thing is the MOSFETs. So obviously 24 versus 36, but these are AOT 290s, and these are another AOT MOSFET. And they are 166916s. So yeah, there's one of those that I unsoldered from the board. That's the differences. If you do a teardown of a BAC8000, you've kind of done a BAC4000 teardown too. I'm betting that the BAC2000 is also once again really similar. That's the big differences here. So, yeah, the connectors are the same. These are some UC brand capacitor. If you can see those on camera, maybe somebody can tell me who makes those things, what brand that is. I don't know what they are. The BAC8000 had Nichicons in it, so there's one of those. I just snipped them all off the board just to get them out of the way. But, Nichicons on here, whatever UCs are, don't know. I don't like this. So you can see these two studs are much smaller than the phase bus or the phase studs. Why they did this, I don't know. Somebody's going to wrench on these ones and they're going to hold up, and then they're cranking on these ones and they're going to shear them off at the solder line. Probably won't rip up the board any because these are really well supported, unlike say with an MCPCB, like say KO Moto or Suron or Teleria has. Where those ones you will rip up the traces. These ones you're probably just going to break the solder off. But repairability on ASI controllers is pretty damn low. So, yeah, having these be small studs like that, I'm not overly fond of that. That's asking for some gorilla to break something off. This board is exactly the same. So here, let me pull this back a little bit. There we go. There's the BAC8000 board. We'll flip that over. And here is the BAC4000 board. I am not going to pull this off. This is a, sorry, I've got it flipped upside down. This is a functional controller, or was, with the exception of a broken off pin over here, and then I have sheared off that inductor. And I've also broken a leg on a MOSFET. So some minor repairs, and this BAC4000 should be running again. Whereas the BAC8000, which was totally brand new, I knew that it was going to be a destructive teardown, so it's going to stay destructive. But yes, I want to try to get this BAC4000 back up on its wheels again and running. So I'm not pulling this off because, well, that is pretty much a guaranteed failure waiting to happen. Yeah, repairability on these controllers is not super good. I had to pull this out. I had to, because that's the only way I was going to get to this connector. So you can see that broken off pin right there. Yeah, that's the reason why this was sent to me. Because, yeah, repairability on these things is excruciating at best. And, yeah, I need to unsolder this connector right here. So I can take that out, and I'll probably steal it off the BAC8000 possibly. But, yeah, I had to take it out in order to get at that stupid connector even, to unsolder the thing to replace the broken pin on it. Yeah, and in the process, I also mangled a MOSFET. Which one is it? That one right there, I think. Yeah, that one right there. So, yeah, you can see it's got a broken off leg. So I've got to at least replace that one AO290 MOSFET before I can even get this thing running again. So, but that's how it goes. That's ASI. They do not want you repairing their hardware, period. They don't. Okay, BAC8000, BAC4000. You can see the MOSFET legs. Let's see if I can't get the camera to kind of focus on both of them. Yeah. Anyway, yeah, you can see how they're using the skinny portion of the leg. And here's the BAC8000 doing the exact same thing. And these are two TO220 MOSFETs. The fat portion of the leg is rated for 75 amps and the skinny portion for 50 amps. If you run the MOSFETs at close to their ratings and you're doing it off the skinny portion, you're going to make a lot of heat in the legs, and that's going to translate to heat inside the MOSFET. And you don't want that. You want to use the most efficient current path into the and out of the MOSFET as possible, and that's the fat portion of the leg. So, this isn't great. Never was. Still don't like it. And here it is on the BAC4000 doing the exact same thing. This isn't cool. They should have these MOSFETs soldered all the way down to the fat portion of the leg on the board. Period. That's just how you do that right. Okay. And they could have done it. You know, it would have required some redesigning of some things, but they could have done it, and they chose not to. All right, let's talk about the things that these two controllers have in similar or common, because it's quite a few of them. All right, so you'll notice right here, my camera, focus on this. Yeah. So this is a little DC to DC converter, and there's a little buck chip for it. You've got a ceramic cap for input filtering, and you've got some more ceramic caps for output filtering. It's probably making 5 volts. And I believe that this is a secondary 5-volt regulator specifically for providing 5 volts to, like, say, throttle and Halls. I didn't realize that's what this was at the time when I saw it, when I did the teardown of the BAC8000, but looking at it on the BAC4000, I went, hey, I know what that's for. So now I've seen 2 controllers with a second 5-volt or DC to DC on it, one for internal and one for external. And I thought it was only eBMX that did it. Here it is on ASI. All right, anyway, that's here. And if we look on the BAC8000, it's here as well. I mean, parts placement is exactly the same. These are clones of each other, just more MOSFETs, essentially. You'll see all this small electronics right here. Well, here it is on the BAC4000 too. And parts placement is exactly the same. Yeah, let's flip this board over. Nothing really else to see on the back side at the moment. I'll get to some things about this in a minute that are different. And on the front side, I am not pulling up this board. I want to repair this one. But, you know, here we go. If you want to see the logic board, here it is. It is the same logic board through and through. Yep. Same Bluetooth module. This one, the wires broke off because they were much flimsier. But, yeah, there's that. Same Bluetooth module. No difference there either. These capacitors, these are made by a company called UC, and this is a Nichicon. I've clipped them all off of here, but it had all Nichicon capacitors on it. I don't know who this UC brand is. I mean, they look physically the same, but they're both 220 microfarad, 100 volts. But, yeah, if somebody knows what that UC brand is, let me know. Underneath this board right here, yeah, I can see, come on camera, focus right here. There we go. I can see all this stuff peeking out underneath there, but all this componentry is the same. By the way, I called that like a mux or something like that when I did this teardown. I didn't look at any of the parts, and I should have done that back when I did the BAC8000 teardown. This is the gate driver chip. That's the gate driver for everything right there. Yeah, there's a bunch of little components. I don't know what these are. I need to look them up. But you can see these here and here and here and here and here. Well, they are also on the BAC4000 as well. Let me get these capacitors kind of stood up. There we go. So you can see one there, and here's another one, and yeah, they're all in pretty much the exact same places on both controllers. I assume those are like an op-amp package. When I do the macro video of this, I will look them up, unlike I did for the BAC8000, and we will have all these parts, and I will use this BAC8000 for all this section right here. So yeah, I'll redo this for the BAC4000 using the BAC8000 board because it is in fact identical. All right, what else I want to show you? Okay, so all these capacitors right here. So you can see all these little ceramic caps on here. Yeah, a gazillion of them. So that's very good. That's going to deal with all the high frequency filtering that you need to deal with. And on the BAC4000, Yeah, let's see, a ton of them in there too. So that's all super good. That's how you want to see it done. Yeah, you've got a couple across here as well. But yeah, there's lots and lots of ceramic caps for dealing with high frequency noise. And yeah, I can't fault ASI for doing this. This is one of the better allocations of ceramic caps. But the only thing that I can say is probably better than this is the, say like the Trampa controllers. That's genuine Benjamin Vetter development. And well, he's a really smart guy and he does really good work. But yeah, this is still pretty good as far as the high frequency ceramic caps. Wish I saw this on more controllers, because this is, that's how you should do the high frequency stuff, folks. Yeah, so like when I don't see this kind of thing, like Far Driver is really lacking in it. Vodal is completely lacking in it. KO Moto is really got a slim selection in it, and they're all down in one end where they're not doing much good. Yeah, those kind of implementations are not very good. The MOSFETs are right here, and those ceramic caps are smack in the middle of them where they should be. And like the Trampa 100-250 controller and the 75-300, they're the same way. The ceramic caps are dead smack in the middle of where the MOSFETs are, where they can do the most good. So yeah, this is good design right here. So on here, I've talked about these current sensors a little bit. So the loops and the current loops on here, and these are doing a very similar job. In fact, they both have a linear Hall inside them. It's just that on the BAC8000, there is no current path interruption happening, and on the BAC4000 there is. So in the BAC8000, you just have a C-shaped piece of metal. It's a bunch of little tiny thin laminations that make a C shape, and then you've got a Hall in it, just like you've seen on, like, say, the KO Motos or the Far Driver controllers, Tellurian, Suron, all use those kind of things. They work well enough for the job. So that's what's in here too. Just that these ones have very thin laminations and a very sensitive Hall in it. This is a slightly different implementation of a linear Hall. So instead, this little piece of C-shaped-ish kind of metal right here, that's copper. And right at the end of it, right there, there is a linear Hall. In fact, you can see it's 3 legs right there. So it's just a different way of doing the same job. These current sensors, I think they're rated for a maximum of 250 amps, and that's like a limitation of this copper cross-section right here. This one specifically, this one's rated for 150 amps, and this is a 24 FET controller. So they are doing a bit of a cheat to use a 150 amp current sensor. Yeah, a bit of a cheat, and let's look at that. So on the back side here, yep, you can see that just fine. So here is the legs for the current sensor, and you'll notice this skinny section right here, and here, and here. What they have done is they have isolated this piece of copper, which is, you know, right at the stud for that phase, from the phase bus, which is here, through these skinny sections. They've created like choke points, if you will, and effectively what they've done is created a current divider. So about 1/4 of the current passes through here for the phase, and then one current, 1/4 here, and 1/4 here, and 1/4 there. So yeah, effectively this current sensor is reading 1/4 of the phase current. I've only ever seen this little bodge done on a prototype controller. Never seen it done on a production controller until I took this apart. And then when I saw it, it's like, hey, I've seen that before. Never thought anybody would actually do it on a production controller, but here it is. Why ASI chose this rather than current loops, I don't know. Yeah, I would have used current loops personally, but whatever. Yeah, let's look at a few other things here. So you can see the MOSFET legs in there, and these are TO220 MOSFETs, and I've talked about this before. The thick portion of the leg is rated for 75 amps, and the skinny portion for 50 amps. And what you should do is solder the MOSFETs in and butt the fat part of the leg down to the board, so that you are using the most current conductive portion of the MOSFET leg. You build up the least amount of heat, the least amount of losses, and all that stuff means heat in the MOSFETs. And here is the BAC8000. doing the exact same thing. And I don't like this here either. You know, I've mentioned this about Vodal. They did the same thing. Yeah, it's just not good design. Yeah, you use the fat portion of the leg. That's the efficient portion of the leg. The skinny portion is less efficient. It means just more heat in the MOSFETs. It's such an easy thing to do. Just solder them down to the fat portion of the leg to the board. That's it. Problem solved. And they didn't do it. So yeah, kind of odd. And here it is in the BAC4000 and the BAC8000 doing the exact same thing. ASI is a bit stuck in the mud. They are. And, you know, even though they could fix this, like, it's good enough. Let's not fix it. You know, that's more trouble than it's worth for us. Yeah. ASI is making themselves irrelevant, in my opinion. Yeah, that's just one of the ways they're doing it. These two controllers are near exactly the same. So you can see right here, all the surface copper, that's all a phase bus. And here's the BAC8000. And it's a little bit wider because it's, you know, got a couple more extra MOSFETs in it. But yeah, you can see the same thing. That's your phase bus all through there. You know, no reinforcing on it in any way. It's fine. This amount of copper is going to do the job, and it's thick enough and it's wide enough that it's not going to be a problem. But yeah, you see the exact same design in here. There's a battery minus and battery plus plane inside the board, and that's true for the BAC4000 as well. You know, this stud right here, as you can see, it's got a circle around it, and the same thing for there. And that's because all the vias take that current path inside the board and not on the surface, top or bottom, really. And you know, here's the BAC8000, and it's the exact same way. There's battery plus or battery minus, I forget which one is which, but yeah, it's completely isolated from any circuit traces here at all. So it's got a ton of vias in there. So they've done that through internal circuit, you know, planes, and that's fine. But I'm just saying, these are clones of each other, just more MOSFETs, that's it. Well, I think that's probably all I want to show on this. Yep. Bigger version of the same thing, that's pretty much it. Slightly different current sensing method. I don't even know if they even had to change the firmware any to do this to this. They probably did a little bit, but yeah, not a lot. Yeah, this was probably like 2 lines of code or something different from one current sensor type to the other, and that was about it. Otherwise, development differences, non-existent, pretty much.